Let's look at a practice problem on rotational kinematics. It reads, a bicycle wheel is rotating at 50 rotations per minute when the cyclist begins to pedal harder, giving the wheel a constant angular acceleration of a half radian per second squared. We want to know what's the angular velocity 10 seconds later, and how many revolutions does the wheel make during that 10 seconds. All right, so again, this idea of kinematics, we can think about a variety of methods that we've already been practicing, some of them. We're interested in this wheel spinning, and from the point of it rotating at a certain angular velocity for that 10 seconds, and what does it look like 10 seconds later. So we're given that the wheel rotates at 50 rotations per minute. All right, so when we're dealing with angular velocity and kinematics, we want to turn all of that into radians per second, so our standard unit for angular velocity. So 50 rotations or revolutions per minute, and we know that they're in one revolution, we have 2 pi radians. And of course, we know in 1 minute, we have 60 seconds. So our unit conversion of 50 revolutions per minute or rotations per minute to radians per second. So we have 50 times 2 times pi, and then divided by 60 gives us 5.24 radians per second. All right, so we have our angular velocity initial. So if we say that we are going to be ultimately interested in how many revolutions, we start our first revolution at 0, and we don't know how many revolutions it's going to make, so that's our delta revolution, delta theta angle. Our initial angular velocity is 5.24 radians per second. Our final angular velocity, we don't know. Our angular acceleration, we're told it's 0.5 radians per second squared. And since I'm talking about a positive angular velocity, and I know I'm going to be speeding up, it says it pedals harder, then my angular acceleration and my angular velocity need to be in the same direction to speed up, and we are given a time of 10 seconds. All right, so we're interested in that final angular velocity, and we know that omega final is equal to omega initial plus alpha times time, our analogy of kinematics equations into rotational kinematics equations, and omega final is simply 5.24 times 0 plus 0.5 times 10. So we get 10.24 radians per second as our final angular velocity. All right, we're also interested, so that's part A, we're also interested in that delta. How many revolutions does it make? And we know that x, this comes from theta final is equal to theta initial plus omega initial t plus 1/2 alpha t squared. So delta theta is equal to omega initial times t plus 1/2 alpha t squared. Omega initial was 5.24 times 10 plus 1/2 0.5 times 10 squared. And we get 52.4 plus 10 squared is 100. Half of 100 is 50, and half of 50 is 25. And so we get 77.4 radians. 77.4 radians. We need to convert that to revolutions. So we know that 77.4 radians, that in one revolution we have 2 pi radians, and so 77.4 divided by 2 pi is 12.32 revolutions in that accelerated phase. All right, so just utilizing our kinematics relationships to obtain our information about angular motion. Good job.